Those power lines carry hundreds of thousands of volts of electricity, and if you were to just plug in your phone or your toaster into one of those lines, it would absolutely obliterate it, frying all the circuits. So what we need to do is we need to take that very high voltage and turn it into a lower voltage, like it does for your house, at about 230, 240 volts, and then even further with one of these bricks for your phone or your computer.
So what is this transformer thing? You can either have a step-up transformer or a step-down transformer, and they're pretty self-explanatory. A step-up transformer takes a smaller voltage and makes it bigger, and a step-down transformer takes a bigger voltage and makes it smaller. So there's three key elements to any transformer. You have your primary coil, which is our input, so it's connected to our AC power supply. We have our secondary coil, which is our output, and then we also have our iron core. If you wanted a step-up transformer, you'd have to have fewer coils on the left-hand side in our input, in our primary coil, and more in our secondary coil, in our output. If you wanted to step down, you'd have more in the first, in the primary, and less in the second. I might as well explain how they work, right? Probably a good idea. So the primary coil is wrapped around some iron core, depending on if it's a step up or a step down transformer. It depends on how many times it's wrapped around. And then it's connected to an AC power supply. Now, alternating current is always changing direction of the flow of the electrons. And this coil creates a pulsating magnetic field. The iron core does not act as a conductor. Rather, it acts as sort of a way to direct the path of the magnetic field between the primary and the secondary coils to minimize wasted energy. Once this magnetic field reaches the secondary coil, it forces the electrons in it to move because of the electromotive force. All right, a bit technical, but electromagnetic induction is when an electromotive force, or EMF, is generated because of its relative motion in a magnetic field. It's the force that the electrons in a conductor experience to get moving. And moving electrons, that sounds familiar, that's just a current. I'm gonna hit you with some more technicalities, look out. According to Faraday's law, the induced EMF in a circuit is equal to the magnitude to the rate at which the magnetic flux through the coil is changing with time. What? That is way too complex. So let's just make it a bit simpler, shall we? So when a magnetic field changes, it causes a voltage. And when there's a difference in electric potential, that can make just electric currents flow. And that's what's happening here in our transformer. Because we're using an AC current, there's the magnetic field and the magnetic flux is always changing, and that's just going to cause a constant voltage. Okay, some more technicality. Lenz's law says that if you place a conductor in a changing magnetic field, it will induce, that's a key word, it will induce a current in such a way that it opposes the original change. If you think about it, it's closely related to the law of conservation of energy. In our transformer, the electromotive force produced in the secondary coil is in the opposite direction to our primary coil, or just a 180-degree phase shift. Hey there guys, so let's just take, for example, Bayswater station to Armidale substation. That's about 290 kilometers as the bird flies, or thereabouts. And let's just say that our transformer is 1 to 1900 coils. That's a nice, neat ratio. And we're putting in 120 volts and 100 amps. To find out what's going to be on the other side, we're going to use two very simple equations. Vp on Vs equals Np on Ns. So that's the voltage in divided by the voltage out is equal to the number of coils in divided by the number of coils out. We've then got 120 from here on Vs equals, well, 1 on 1900. Now we've got numbers we can play with. We're going to flip the whole thing. So Vs on 120 equals 1900. And then just Vs equals that times that, which is 228,000 volts, or 228 kilovolts. I'll put that here, 228 kilovolts. So it's just a few volts, just a few. To find the amperage, we're going to use a similar equation. So Vp IP equals Vs Is. And that's simply just however much current you put in and volts. It's the same on the other side, just different numbers, like a seesaw. So we're going to go 120 volts from here, multiplied by 100 amps from here, is equal to what we've just found. So 228,000 volts multiplied by our current that we don't yet know. That's then 12,000 equals still that. And then we're going to divide that over so we just get Is on its own. And that's going to be 1 on 19 amps. So you can see that it goes in pretty similarly and then just out completely different. It's great. It just means that here we'll have a lot less loss. Let's find that loss now. So power loss is just I squared R, and our resistance is 50 ohms per kilometer. That's what we're calling it. So to find our total resistance, it's just going to be 50 ohms times by our distance, which is 290 kilometers. So that is 14,500 ohms. Our I squared is 1 on 19, so 1 on 19 squared multiplied by our resistance, which is 14500, we get about 40.2 watts. So that's 40.2 joules of energy lost every second. It's a few, but not as much without the resistor, without the transformer. Let's find out what that would actually be, shall we? So power loss without that transformer is still just going to be I squared R, same resistance, but our R is going to our I is still going to be 100 amps. So it's going to be 100 squared times 14,500, and that's 145 million watts, or 145 megawatts. Just compare 40 watts, 145 million watts. So the transformer does a good job at reducing the amount of energy lost in this journey.
Faraday's law. Faraday's law states that electromotive force is equal to negative magnetic flux over time.
And we can see that in a few examples here. For example, a AC power supply that is supplying 240 volts of power at 50 hertz for 60 milliseconds. And you can see here our sine curve, or our AC power supply, because it's an alternating current, you've got negative current as well. And so what you can see here is this pink line, our transformer output, is really just the derivative in calculus of this sine curve, a negative derivative, of course. So when we have, because of our negative here, our gradients of this sine curve of our AC power supply is just going to be our magnetic flux. So that's where we get our negatives in here. And when we get negative here, we're going to get positive here. So when we have the greatest rate of change in our AC power supply, like right here, we'll get a peak. And when we have 0, we'll get a trough, like that again. But when we have 0 here, again, trough and peak, we'll get the greatest rate of change. And this one is literally just the same as this. It's got the same power supply, but we're rectifying it. So we're just making the entire thing positive. And that's why it bounces like that. And we're going to get the same output because of this. We're still coming from an AC power supply, so we're still going to have that constant change. And because we've got literally the exact same one, we're going to get this consistent curve like we did up here. And when we've got and when we've got here being 0, when our gradient of this is 0, we're going to have the greatest rate of change. And so that's why he's going through the x-axis here at the highest. Here we've got the greatest rate of change, so we're going to have a peak, same here, trough, peak, and we'll just do that forever, but we're stopping at 60 milliseconds.
So here we have our 12-volt DC car battery. As you can see, its input is relatively quick and it stays level after it reaches its 12 volt. That is because it is a DC car battery. It's, as a battery, consistently outputting 12 volt. Unlike this rectified DC, which has peaks and troughs, this is a continuous line. It peaks and then stays there. And so as Faraday's law states, for induction to occur, the magnetic force influenced by this 12 volt DC car battery needs to be continuously changing, increasing, decreasing, oscillating for induction to occur. And so as the DC car battery voltage levels out and remains the same, your transformer output peaks and then nosedives down again. And that is because there is no more magnetic flux. It remains the same, it does not induct.
No transformer is perfect, and there's so much loss that could happen and does happen due to leakage or like warmth or things called eddy currents. Now, eddy currents are currents that circle around in conductors like swirling eddies in a stream. They are induced by changing magnetic fields and flow in closed loops, perpendicular to the plane on the magnetic field. The eddy current's magnitude can be reduced by designing the core as a set of thin sheets or laminations in parallel to the magnetic field. By laminating the core, the area of each section and hence the induced EMF is reduced. Ideally, all the flux will link with both primary and secondary windings, but in reality, this is just impossible. Although maximum flux will link with both windings through the iron core, there will still be a small amount of flux which will link to either winding. This is called leakage flux. Due to this leakage flux in the transformer, both primary and secondary windings will have leakage reactance. You can reduce this leakage by putting both primary and secondary windings as close to each other as possible, like that. It is generally done by placing the secondary coil over the primary coil in the same limb in an insulating separating both windings, like this one.
And that's been transformers. They do a really good job at taking a very big voltage and making it small, or doing the other way around, making a small voltage very big. And they're really easy to make. You can make your own. You just get a C-hook thing, wrap some wire around it, attach it to an AC power supply, and bam, you've got yourself a transformer. They're not hard to make, and what little improvements you can do affect it. The eddy currents and the magnetic flux leakage, they're not hard to fix. They're quite easy. So why not use transformers? You reduce loss, and who wants loss in efficiency? Transformers, they're pretty good.